So having talked about the classification of bone, both by composition and by shape, let's move on and talk about the histology of bone. Remember, histology means the study of tissue. So bone is a type of connective tissue as seen by widely spaced cells separated by matrix. The matrix is roughly 15% water, 30% collagen fibers, and 55% crystallized mineral salts. Now the word salt, if you've taken some chemistry, you know that doesn't just mean table salt. Lots of salts, all right? So sodium, potassium, chloride, bromium, those can all form salts. That's a general name in chemistry. We won't go into it any further. Most of the mineral salts are in the form of hydroxyapatite, and that's the one we need to know. It's a crystallized calcium phosphate salt. And there you see the actual chemical formula of it. You don't have to know that, but just showing you it's calcium and phosphate, and you've got a bunch of OHs, a bunch of hydroxyls there, 2 of them. So the mineral salts are deposited in a framework of collagen fibers, a process known as mineralization or calcification. So first you have to put down the matrix of the bone. You can see in the upper illustration there in the center. That's basically the collagen matrix, and then into that matrix the mineral salts are deposited. That's what bone is made of. So the hardness of bone depends on the mineral salts, the hydroxyapatite, the calcium, and the phosphate. The flexibility depends on the collagen fibers. I'd say it's like fiberglass. They used to use fiberglass to make expensive cars. You see there over on the right. They still do, fiberglass for insulation. Fiberglass is fiber and glass. So the glass makes fiberglass tough and hard. The fiber makes it flexible. It's the same in your bones. Bones have to have flexibility. You don't think of them as being that way, but they are. I'm listening to Renaissance music, and it just came up a little in volume. Let me shut that down. So, yeah, like if you jump up and down, and we used a super slow-mo camera and looked at your leg, we would see that your leg flexes a little bit when you hit the floor. And that's necessary. What would happen if your bones didn't have flexibility? You would be breaking bones all the time. So flexibility is necessary, all right? You have to have both. It's kind of like your personality. You got to have some hardness, you got to have some flexibility. Really common theme in nature, all right? Bones have to be that way. So where does skeletal muscle attach? Articular cartilage, endosteum, fibrous layer of periosteum, osteogenic layer of periosteum, or medullary cavity? These are the kinds of questions I use on quizzes and exams, so expect to see something like this in the future. This was easy, wasn't it? It's the fibrous layer of the periosteum. That's where the muscles attach. It's the osteogenic layer where new bone tissue is formed. So let's look at bone cells. There are 4 basic bone cells, and they're in 2 completely different categories. So let's try to keep this straight as we go through, all right? It's not that hard. So osteogenic cells are stem cells. They are the creators of bone tissue. They can divide to replace themselves, and then they can become osteoblasts. And in Bio 156, you should have seen a few different kinds of blast cells. Blast cells often form the matrix or they're essential in forming new growth, new tissue. You see lots of blast cells in the body. So osteogenic cells divide to keep making themselves. That's why you won't ever run out of bone, because they keep making new stem cells. But then they can also make the osteoblasts. And what do the osteoblasts do? The osteogenic cells, of course, are found in the inner layer of the periosteum, the osteogenic layer. They're also found in the endosteum, because bone has to grow from the inside of the medullary shaft as well. The osteoblasts form the matrix and the collagen fibers, but they can't divide. So osteoblasts are interesting. The cell basically starts making a matrix of collagen fiber around itself, but then it ends up getting trapped inside of it. So that's its job. It functions in what we call bone deposition, laying down bone. We deposit things into the bone. We deposit a collagen matrix and minerals into the bone. That's called bone deposition. That's the formation of bone. That's an important term. We need to know that one. Bone deposition. Osteoblasts do bone deposition. Then what happens is, remember, the osteoblasts are building the matrix, but they can't divide. So after they're done, they get trapped inside. It's kind of like a person. It's like you built a shed around yourself, but the shed doesn't have any doors. So once you finish building the shed, you're trapped inside. That's what happens to the osteoblast. Then it finishes its maturation and becomes an osteocyte. So osteocytes no longer secrete the matrix. They're trapped in the matrix they secreted. All right? So that's one line of cells. Notice the osteogenic turns into the osteoblast, which turns into the osteocytes. So those three cells are closely related because one turns into the other and then turns into the other. A completely different kind of bone cell is an osteoclast. These are big, giant cells made from like 50 monocytes that fuse together. Monocyte is one type of white blood cell. We'll see there are 5 kinds of white blood cells. Monocytes are one. Whole bunches of them fuse together. Monocytes are the cells, the white blood cells, that turn into macrophages. They eat stuff. So these osteoclasts are huge. They're monstrous cells. 50 fused monocytes. And what do? They eat bone. So they function in bone resorption. This is where you actually dissolve bone in order to return the minerals to your body. This is what a part of homeostasis. Remember, I told you several times homeostasis is the main topic in this entire class. So at some point you need to put minerals into the bone. You need to make bone, all right, in order to function. But then if you run low on those minerals, you can pull them back out of the bone and put them back into the blood. So osteogenic cells, osteoblasts, osteocytes, those are all involved in building bone, putting minerals into the bone, and then osteoclasts pull the minerals back out. That's bone resorption. So bone deposition and bone resorption are the opposite of one another, and you need to have both of those occur in order to maintain mineral homeostasis. Okay? Now let's zoom in and take a really close look at compact or dense bone. Looks like a solid, hard layer of bone. Makes up the shaft of long bones and the external layer of all bones. I've mentioned that a few times so far. It resists stresses produced by weight and movement. So compact bone is very good at supporting your body. It's what when you stand on your legs, you're standing on big shafts of compact bone. That's strong stuff designed to keep you upright. So looking then, zooming in a little closer, compact bone is arranged in these units called osteons. Old-fashioned name was Haversian systems. Osteon is a newer name. So see those concentric circles? They look kind of like bullseyes. Each one of those is an osteon. And then notice one of the osteons they've telescoped out so that you can see osteons are made up of rings of bone. Okay, so do you see? Like in the upper left of that bone, there's 1, 2, 3, 4 bullseyes. Then there's another bullseye down below, that telescoped one. Each one of those structures is an osteon. That is the fundamental unit of compact or dense bone. Osteons contain blood vessels. Why? Why do they have to have blood vessels? Because bone tissue is alive. It needs oxygen and glucose so it doesn't die. And how do the tissues of your body get oxygen and glucose? They get it from the blood. There are also lymphatic vessels. We'll talk more about that in Bio 202, that recovers fluid. There are nerves. Bone is living tissue. You need to know if something goes wrong, so there are nerves to let you know, nerves that convey pain. Also nerves that stimulate various processes in the bone. And then the osteocytes are in the calcified matrix. Osteons are aligned in the same direction along lines of stress, which can slowly change as the stresses on the bone change. So in other words, the osteons of your leg bones are arranged vertically. So they provide they're like columns, they're like big pillars that hold you up. But they can change slowly. So for example, if as you're growing, if you don't get enough calcium in your diet, the osteons may not be able to support you, and they end up starting to bend, and then you get bow legs. That's called rickets when that happens due to a nutritional deficiency. So compact or dense bone. Continuing then. Ooh, I talked over the transition. I'm never supposed to do that. Sorry. So the osteon is composed of concentric rings, all right? So each one of those rings is called a lamella. Plural is lamellae or lamellae of calcified matrix. They're vertically oriented with a central canal in the middle. So can you see there the central canal? We see real bone tissue in the illustration on the top, and then we see the cartoon over on the bottom. But you can see those central canals, they have both the bones and they have the nerves. So the blood vessels and the nerves. Blood vessels to supply the nutrients, nerves to give information about what's happening inside the bone. Then there are also perforating canals that run perpendicular to the central canal and carry blood vessels into the bone and marrow. So in the bottom right illustration, see how there are blood vessels that run sideways? You can see the vertical blood vessels inside of the central canals, but then see how those are connected by the perforating canal? Blood vessels run sideways as well. That way blood flows easily throughout the bone tissue, and that's what you want. You want blood to flow very easily because blood is carrying nutrients to the cells of your bones and it's carrying waste products away. So you want blood to flow freely through a bone. That's what the central canals and the perforating cells working together can accomplish. The osteocytes are found in spaces called lacunae. So in the upper illustration on the right, you can see the big central canal, right? Then see all those other little black spaces? All right, see there's bunches of them, and they go in rings. Remember, each ring is a lamella, and kind of around the edges of the lamella, you see those little black oblong spaces? Those are called lacunae, singular lacuna, plural lacunae. In Latin, that means a little lake. And you know, the fluid inside of your body, you're full of fluid. Your body's roughly 50% water. So most of the inside of your body is water, half of it. And so it really is true to say they're like little lakes, all right, because they would be filled with fluid, all right? Those are the lacunae. Now, osteocytes are living cells, and each osteocyte lives inside of a lacuna, all right? Each lacuna has one osteocyte living inside of it. So what's going to happen here is osteocytes, being living cells, they occasionally need to talk to other osteocytes. So how can they do that? Well, notice in between the lacunae, see how they're little thin dark lines? Those are little tiny canals that connect the lacunae. They're canals that connect the little lakes. So they're called canaliculi. Canaliculi means a little canal. So you see what happens is that an osteocyte, if it needs to talk to another osteocyte, it basically writes out a message, then puts it in a little bottle, drops it into one of the canaliculi, singular canaliculus, and then it floats over to the other lacuna, and then that osteocyte can pull the bottle out and open it up and look at the message and say, "Oh my gosh, you broke up with Jennifer? I'm so sorry." Well, no, actually, she was, well, whatever. So, yeah, see, that's how they can communicate and talk to each other. And there are also these things called interstitial lamellae, not a big deal, but what happens is as bone continues to grow, as you modify bone, you'll end up with lamellae that are not perfect concentric circles. They're kind of like filling in the spaces. Those are called interstitial lamellae. Interstitial means basically in the spaces, so don't worry about that too much. Now, that was compact bone. Let's take a look at spongy bone. In many ways, it's very, very similar, but there's also a big difference here. So it generally does not contain osteons. So look at the upper right there. You can see there you've got spongy bone. You've got the lamellae still, right? All right, lamellae, remember, are the bony rings. There are still canaliculi. There's still lacunae, all right? But there's no osteon. There's no central canal. And you might be thinking, WTF? Why doesn't it have a central canal? Well, remember, what was the central canal for? It was for nerves, also for blood vessels, because you had to bring nutrients to the bone, and nutrients are carried through the body by your cardiovascular system, by your blood. Well, remember what happens in the spongy bone? Remember what we have? What's in those spaces? See in the upper left there, see all the spaces? What's inside of all those spaces? That's red bone marrow in there. So red bone marrow has got tons of blood cells in it, so you don't really need to have a central canal. You've got plenty of red blood cells all over the place anyway. That's why you don't have to have an osteon, okay? So instead, spongy bone has this lattice work of thin plates called trabeculae, singular trabecula, plural trabeculae or trabeculae. So in the upper left, each one of those little projections, each one of those little things sticking out is a trabecula. And those form basically the sort of framework that the red bone marrow is inside of. Trabecula really means like a strut or a beam, kind of like a 2x4. So see, use your imagination. On the upper left, it's like lots of 2x4s that are enclosing a hollow space, and that hollow space has got the red bone marrow inside. It provides strength with little weight, so the trabecula are actually very strong. Remember we showed that picture earlier? So it looked like somebody hit somebody on the head with a hammer. The spongy bone actually absorbed that impact, so it's pretty strong stuff, but it's not very heavy. And the spaces in between the struts are filled with red bone marrow where blood cells develop. As I've said several times, central canals, you don't need them because no osteocyte is far away from the red bone marrow. Therefore, oxygen and glucose can simply diffuse through the red bone marrow to the osteocytes. And where do you find spongy bone? It's found in the epiphyses of long bones. Remember, on the end of the shaft. The shaft was a diaphysis, the ends were epiphyses. It's found on the inside of flat bones, such as the hip bones, os coxa, the sternum, the sides of the skull, your parietal bones, and also your ribs. When they do a bone marrow transplant, they have to go into the bone, into the spongy bone, and that's where they can get the bone marrow to do the transplant. No osteons, okay? No osteons. That's spongy bone. So take a look here, just kind of a summary picture showing it all. In the upper right, you see the compact bone that has the osteon, made of the osteon, has the central canal. And then on the lower half of the illustration, you see spongy bone. All those trabeculae with the red bone marrow inside. And of course, there are still blood vessels that are running in there in order to make the red bone marrow. But lots of red blood cells in the red bone marrow, okay? The trabeculae of spongy bone, and you can see canaliculi opening on the surface as well. So here's a little critical thinking exercise for you. I want to know, each one of these pictures is basically suggesting a particular type of bone cell. So let's look at the upper left. What kind of bone cell is being represented there? These guys have painted themselves into corners. Yeah, that's an osteoblast. Remember, it makes the matrix and then it's trapped inside of the matrix that it made. So that's an osteoblast. What about the bottom left? What am I going for here? Those look like long stem wine glasses. Long stem wine glasses. Yeah, so those are osteogenic cells. Those are stem cells. All right? Is that goofy or what? What about the upper right? Fused. All right? Fused. What would that be? Yeah, osteoclast. Remember, like 50 or so macrophages or monocytes all fused together to make an osteoclast? And then in the lower right, oh my gosh, we've got a living thing trapped inside. What is that? It's now mature. It can't get out. That's the osteocyte, trapped there in the matrix, trapped in the little lacuna. Probably would have been better if I had a picture of someone trapped in a lake, but I don't know. I'll see if I can improve that for next semester. And here, let's continue. What do we have in the upper left? What do you suppose I'm trying to get at there? We've got these ring-like things. Yeah, those are lamellae. Rings of bone in your body. Here, that's actually pretty cool. Those are different oils in a bowl, and so the thickest oil's gone to the bottom, the lightest oil's on the top. Pretty cool. What about the lower left? Yeah, Venice. The canaliculi, the little canals. What about the upper right? The lacuna. Yes. And what about the lower right? The 2x4s, the struts, the beams, the trabeculae. Okay? Wasn't that fun? Don't say yes or no. Just keep it to yourself. Okay, we're done with this one. On to the next PowerPoint of bones.